be reviewing concepts and applications of remote sensing for crop management. So this is the proposed agenda that we have today. First, we're going to review how this works. It's very simple concepts, very complex technology, but very simple to use. Then we'll see some of the options we have. There's a lot of options in different resolutions and different characteristics. UAVs, traditional satellites with different resolutions. Now we're coming. The time is coming for nano satellites, and we'll see what that is all about. Then we'll review some sample cases. GeoAgro has been applying technologies for 10 years, or now 11. And in Africa, more than 3-4 years now. And so we have had quite a few experiences in showing how this, or experiencing how these technologies can help crop management be more effective. So we'll be reviewing some of those cases. The best known index that you can use from remote sensing is Normalized Differential Vegetation Index, NDVI. But there are other indices that are being used, so we'll also review those concepts and some sample cases, and what we can expect to see in the next years as upcoming innovations. Okay, we'll start with basic concepts. The basic concept is very simple. When we talk about remote sensing, really, I didn't want to make this complicated, but you have maybe more than 10 type of sensors. You have active sensors such as a radar, which broadcasts a signal and it receives the reflected signal, or LiDAR or laser sensors. Those are active sensors, or thermal. Well, thermal is passive, but you have the concept of an active sensor which broadcasts any type of signal and then receives the response, such as a laser measurement or a radar measurement. But we're going to focus only on passive systems on detecting radiation. So the concept is very simple. It's you have sunlight that reflects on different types of objects, and the satellite is very well prepared with sensors that captures that radiation, that reflected radiation, in different ranges of waves in order to get more information about the objects that are being analyzed. So, as you know, the light it's a phenomena that has, or better yet, there's an electromagnetic spectrum which we can analyze in order to capture different ranges of bands of reflected light. It can be decomposed in different ranges, light or other phenomena. When you talk about light, you're talking about a certain range of reflection, which is shown here for 400 to 700 nm. And then you have all the range of waves that we use, such as the radio waves, or all the way down to gamma rays, which are very short wave mechanisms. So based on the wavelength, we can determine different aspects. We're going to focus only on the visible region, that is how light is decomposed, and also on the infrared, which is something that's not visible to the eye, but that's very relevant, as we'll see, for crop management. So those are the areas that we're going to focus. And the interesting thing about plants is that through the photosynthesis mechanism, they can absorb light in certain ranges, which is the visible range, depending on which helps us determine the amount of chlorophyll, which is the element that helps in that absorption. And also the amount of biomass has a characteristic that it reflects the near infrared. So with those two concepts, plants absorb light and they also reflect depending on their biomass. We're going to measure two things: how much of that visible range disappears, how much is absorbed by the plant, and how much near infrared wavebands is reflected. So just to make it very graphical, this is a basic concept. Let's say vegetation with a good amount of biomass is going to absorb more of the visible light and is going to reflect more of the near infrared range. And plants, or let's say when they have health problems, or maybe when they have not grown yet, they will absorb less visible light, and they will reflect less. I mean, they will yes, they will absorb less, so they will reflect more visible light, and they will reflect less near infrared. So many years ago, I think in the 60s, in university research, they came up with a way to measure crop biomass, which compares those reflectance values, and based on that relationship between near infrared and the red visible spectrum, they came up with a range of values between -1 and 1. As you can see in this example, in this healthy plant, it's 0.72. In this unhealthy, it's 0.14. So that can help identify areas of varying levels of plant vigor within fields. And another aspect is that different types of plants, they will have the similar behavior. So you see here in this visible range, they absorb. In this near infrared, they reflect. We have the reflectance there. And they will have different levels in those values, depending on whether it's a grass that we're analyzing, wheat stubble, alfalfa, beans, corn, or soybean. So that will depend on the plant form. Okay, so that's a very quick introduction with the purpose of showing that it's a logical mechanism. It's something that has been researched, and now we're using it for very practical applications. So NDVI, which is which is the index that's mostly used. There are other indices, as we'll see. It's a good management tool for a number of reasons. It has an important relation with crop yields data at a certain point in the crop chronology. We'll see that's between 45, 60 days before harvest in certain crops such as corn, wheat, sunflower. It can provide record of vegetation coverage and changes during a different time period, and we'll see very practical application of that. It's related to phenological vegetation patterns, so we can draw a curve that more or less will repeat itself in different crop seasons for the same crop and variety in the same region. And it's indirect measurement, it's unbiased, it's cost effective, and you don't need to go to the field. So it's a good management tool. Not only NDVI, it gives an indication, but it's a good support tool. So just to give more practical idea of how this works, you will see that there's a relation between NDVI and the phenology, the type of crop and the phenology. So this is, all these charts are for Kansas. And we see that, for instance, alfalfa repeats the same curve. It will have different variations depending on weather and also depending on planting dates, of course. Here we see wheats. So for the northern hemisphere, yes. Yeah. Mike, is everything coming out okay?
And I can hear you fine. I haven't heard any audio issues so far.
Okay. Okay. So you're seeing the wheat screen phenology. You'll see there northern hemisphere, a crop season that develops between March and July, the most active crop activity. There's summertime, and this shows how NDVI evolves in the crop wheat, and this is related with the crop phenology stages. So we can have different stages, and we can have a more or less expected NDVI value. So you can see that the crop is growing, has a higher biomass, then comes flowering, and the crop starts to wither, and then the biomass starts to go down, and and we can follow that evolution through this NDVI values over time. Again, we have another example for corn, which is have a higher mass and biomass in July in their season, and then soybeans. So this is an important aspect to keep into account, and you'll see that this will be useful to compare how crops are behaving in different seasons. NDVI and weather, of course, it has a huge incidence. This is an example from the U.S. Department of Agriculture analyzing the South African crop season in 2011 and 2012. Now, this was interesting in the sense that it was expected to be a wet year. It was a La Nina year, but they had unexpected low rains in those years. And Francis, you can correct me. I'm just getting this data from USDA, and you have the field experience in those years. So please let me know if it's making sense. So you see here again, you can translate those -1 to 1 values, color in red to green. And you see here in April 2011, you have above average crop conditions before harvest, and you have in the year 2012 below average crop conditions before harvest due to scarce rains. We can see this in a time series. So you see this is the average for 4 provinces: Northwest, Mpumalanga, Free State, and Gauteng. And you'll see in yellow the curve that's showing the NDVI average for the province in 2011, and in red the average for the 2012 year. So you can see the lower biomass due to scarce rains. And again, even though it should have been wetter than usual years, those were drier than usual years. So there they have the corn yields going below the average trends. Okay, let's see if we have any questions. No questions so far. Okay, so that's 2 aspects: phenology, weather, and again yield correlation. We see time and over time. GeoAgro Africa, as you know, supports farmers in being more effective in managing their crops, lowering the risk, improving yields. So we process different types of data. We process a lot of imagery data, and we process a lot of ag equipment from applicators or from yield monitors. So we see this pattern repeating over and over between 45 and 60 days before harvest, if we have a more or less normal year without no extreme events. In most of the extensive crops, canola, wheat, sunflower, corn, sorghum, we see that there's a very close visual relation between NDVI and yield. So we have in this map the NDVI, this is in Argentina, December 27th in sunflower. So we have here the values of NDVI. And then we have that same field that was harvested with a yield monitor with values ranging from 1 to 5 tons per hectare. We see that the NDVI pattern that we're seeing now, it's very similar to the yield pattern. So it's a very good indicator of 45 to 60 days before harvest of how yields are going to perform. And we'll see an example